Hi everybody. Today's section is going to be on 11.5. We're finally going to stray away from positive series and we're going to talk about alternating series. So what is an alternating series? An alternating series is a series whose terms are alternately positive and negative. And I'll give you some examples. First, I have a series that looks like this. So 1 minus a half plus a third minus a fourth plus 1/5 minus 1/6, and so on. Okay, another one would be maybe something like negative 1/2 plus 2/3 minus 3/4 plus 4/5. And you can see the pattern there. How would you actually write these series down? Well, this first series, we could see the pattern is 1 over n, except it is alternating between negative and positive. So the way that we make it alternate between negative and positive is you take a negative 1 to the power of something. In this case, because the first term, we know we want to start at n equals 1. And so, let me erase this a little to give myself some room. If I put a negative 1 to the n here, then that means that the first term is going to be negative, right? Because I have negative 1 to the first power. So I write n minus 1 to adjust for that. And so this is how I would write the first series. The second series, I can write it as, we could see the pattern, right? The top is n and the bottom is n plus 1. So it's n over n plus 1, right? But the negative 1, this is going to be to the nth power because the first term is actually negative here. So we notice something. Are these the only two possibilities then if we have negative 1 to the n minus 1 or negative 1 to the n? The answer is yes. All alternating series have that form. So let's write this down. All alternating series have the form negative 1 to the n minus 1 times bn, or negative 1 to the n times bn, where bn is greater than 0. So what is bn? Bn you could think of as if you strip away the minus sign, you're left with the bn. So in this problem, the bn is 1 over n, right, for this first example. And for the second example, bn is equal to n over n plus 1. Okay? Let me just write this a little more clear here. This is an is equal to one of those two things, right? So notice also that if you take the absolute value of an, you just get bn, right? So the important thing here is the first term, right? The first term tells you if the first term is negative, then it's going to look like this, negative 1 to the n. And if the first term is positive, then it's going to be negative 1 to the n minus 1. Now, unfortunately, the series tests that we've come up with before are not going to apply to an alternating series, right? Because we've got the integral test and the two comparison tests. All three of those actually require for the series to be positive. So if we have an alternating series, we do need a different test. So that's what leads us to the to the test that we're about to learn, which is called the alternating series test. This is called the alternating series test. I abbreviate it AST. Okay, here's the test. Suppose this guy or this guy is an alternating series. Doesn't matter which. Okay. Suppose the following two conditions are satisfied. First, bn plus 1 is less than or equal to bn. And I'll say eventually. We care about what happens in the long run, okay? Another equivalent way of writing condition 1, by the way, is that bn is decreasing. Condition 2, suppose that the limit as n goes to infinity of bn is equal to 0. Remember, we're just looking at the positive part here. If both those conditions are true, then the alternating series is convergent. Okay. I'm not going to prove this theorem just because of a lack of time here, but what I do want to say, I just want to give sort of an outline of the proof, okay? So I'll say proof outline. Let's just say that our series looks like this, negative 1 to the n minus 1 bn. This is the same as having b1 minus b2 plus b3 minus b4 plus b5 and so on. So here's what we have. Let's suppose that 0 is right here, and you start by writing down b1. b1 is some positive number, so let's say it's right here. Now you subtract b2 from it, but remember, we're supposing that the sequence is decreasing, so b2 is smaller than b1, right? So this means that if this is b1, this is b1 minus b2. What happens next? We add b3, but now that has to be even smaller. So there you go. Now you can imagine what's going to happen if we keep doing this, right? The idea is that we're actually going to keep getting closer and closer to a number. Now, of course, it could just bounce back and forth forever and never actually approach anything. However, it's the fact the second condition tells us that the limit as n goes to infinity of bn is 0. This means that terms eventually get super small, And so this shows that eventually we are going to end up hitting something. That's the idea here, guys. So eventually we are going to converge to some number in the middle, right? Some number in the middle. Okay, so all we need to do is show that both of these two conditions are met. So let's go ahead and do an example. This will be example 1. Study the series. And we're going to look at the one that I already wrote down. How about that series? 1 minus a half plus a third minus a fourth plus a fifth, and so on. So in other words, this series looks like this. Negative 1 to the n minus 1 times 1 over n. And n is going from 1 to infinity. So in this series, Bn is 1 over n. So that's what we're going to look at, right? So we're going to use the alternating series test. Let's look at condition 1 first. Bn plus 1 and Bn, we want to compare that, right? Bn plus 1 is 1 over n plus 1, and Bn is 1 over n, and it should be clear that Bn plus 1 is smaller than Bn. Well, I guess all we really need is for this to be less than or equal to. Certainly true, right? And we don't need to do any further check here because this is obviously true, right? The denominator of 1 is larger than the other, so it's clear that it's smaller. What about condition 2? Well, we just need to do the limit as n goes to infinity of 1 over n. Well, this is just 0. So both conditions of the test are met. So by the alternating series test, the series converges. It's that simple. This is actually one of the easiest tests to use because all you have to do is show two things, and then it's not that you get that they're similar to something else. No, you just get that it converges. Okay. Okay. Before we move on, I do want to revisit our divergence test and make it a little bit better. So let's revisit the divergence test. What I want to do is I want to create a new test called the strong divergence test. This is an even better version of it. Okay. The strong divergence test says as follows. If the limit as n goes to infinity of the absolute value of an is not equal to 0, then the series diverges. What's special about this test, the reason I call it the strong divergence test is because of that absolute value. Now, something interesting about the alternating series test, remember we have two conditions. This condition actually looks like the alternating series test condition, doesn't it? If we look at the alternating series test condition, this is basically the opposite of condition 2. So this leads me to say the following. Note, if condition 2 of AST fails, the series diverges by the strong divergence test. So it's important for you to cite this correctly, okay? It's not by the alternating series test. Let's say you are doing a problem and you're trying to check these two conditions, and then you notice that the second condition is not true, that the limit is not 0. At that point, you would stop and you would say, by the strong divergence test, the series diverges. Okay? All right. So let's do some more tricky examples, right? That one was pretty simple, the one that we just did. So let's do another example. Problem 2. Let me write the instructions the way I've been doing it. So we're going to study the series. And it's going to be -1 to the n, 5n over 6n plus 2. And n is going from 1 to infinity. Again, we have an alternating series, so I'm going to use the alternating series test on it. So let's use AST. What is Bn? Bn is, just take away the -1 to the n part, it's over 6n plus 2. Now looking at this, I can immediately tell that this limit is not going to be 0. And so if I try condition 2, and I do the limit as n goes to infinity of 5n over 6n plus 2, I actually get, if I divide everything by n, over n, I end up with the limit as n goes to infinity of 5 over 6 plus 2 over n. And this bottom guy goes to 0, so this whole limit is equal to 5 over 6, which is not 0. So at this point, I change gears and I just say, by the strong divergence test, the series diverges. Okay, so sometimes you'll be trying to use the alternating series test, but you will notice right off the bat that the limit does not go to 0, and so you can just cite this and you're done with the problem. Okay, guys, let's do a more interesting example. Problem 3. Study the series This one's going to be a little more complicated. So this is our series. It's -1 to the n plus 1, and then n squared over n cubed plus 1. So again, we are going to use the alternating series test on this. So Bn would be n squared over n cubed plus 1. So we are going to have to do both conditions. First, let's go ahead and check Bn plus 1 and Bn. So Bn plus 1 is n plus 1 squared over n plus 1 cubed plus 1, and then Bn is n squared over n cubed plus 1. Now, I'm hoping it's clear here that it is not obvious which one of these is bigger, right? In the other example, just to backtrack a little bit here, when we did example 1, it was obvious because in example 1, this guy had a bigger denominator than this guy, but the numerators were the same, and that's the key here. The numerators were the same, but in this other problem that we're working on, the numerator of the guy on the left is bigger, but the denominator is also bigger, so it's not clear which fraction is bigger. So we are not going to be able to just make a decision here. What we need to do is we need to use derivatives to do this. So let's do that on the side. Let's let f of x equal x squared over x cubed plus 1. Let's go ahead and take a derivative. So remember, the derivative of this, we need to use the quotient rule. It's going to be the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So this gives us 2x to the fourth plus 2x minus 3x to the fourth over x cubed plus 1 squared. So if we simplify the top, this means that f prime of x is equal to 2x minus x to the fourth over x cubed plus 1 squared. Let's go ahead and set this guy equal to 0, right? If we write 2x minus x to the fourth equals 0, we can factor the x out and we get 2 minus x cubed equals 0. So this gives us x equals 0 and x equals the cube root of 2. And if we set the bottom equal to 0, we actually get x equals negative 1, right? And so if we look at our derivative chart, remember, we just care that even though our derivative might change sign at these values, we don't actually care. The only thing we care about is what happens eventually, right? So we're going to plug in a number that's bigger than the cube root of 2. How about 2? What's f prime of 2? So f prime of 2 is equal to, on the top we get 4 minus 16, and on the bottom we get 9 squared. In other words, we get negative 12 over 81, which is clearly a negative number. So this means that our function is decreasing after the cube root of 2. So what we just showed is that Bn must be decreasing also. Let me write that down here. Since f of x is decreasing on cube root of 2 to infinity, Bn is decreasing also. In other words, all of this was condition 1. We're done with that. Okay, so condition 2. This is the easier part. Let's just take the limit as n goes to infinity of n squared over n cubed plus 1. Again, divide by the largest power of n in the denominator, which is dividing by n cubed. This gives us the limit as n goes to infinity of 1 over n over 1 plus 1 over n cubed. And this guy goes to 0, this guy goes to 0. 0 over 1 is 0. And so we get both conditions are met. So by the alternating series test, the series converges. Okay, so I want to do one more example, and this example is going to tie into the next thing we talk about. So let's look at number 4. This example won't be as hard as this one, but it will be an interesting display. All right, so let's look at number 4. We're going to study the series Negative 1 to the n over n factorial. In case there is confusion about n factorial, just to be clear, for example, 5 factorial is 5 times 4 times 3 times 2 times 1, or 3 factorial is 3 times 2 times 1. So this is how you define a factorial. 1 factorial is just 1, and by the way, 0 factorial is also 1. We don't define it for negative numbers, okay? But anything besides 0 or 1, you just multiply down until you get to 1. So how would we do a series like this? Well, we're going to use AST on it, and of course Bn would just be, take away the negative 1 to the n, it's just 1 over n factorial. Don't let the factorial scare you. This is actually going to be quite an easy problem, right? Because 1 over n plus 1 factorial and 1 over n factorial, this is clearly smaller than that, right? So this implies that Bn is decreasing. So that part's easy. Condition 2, the limit as n goes to infinity of 1 over n factorial. Clearly, the bottom number grows large, the top stays the same. This is just equal to 0. Both conditions hold. So by AST, the series converges. Okay. Now, there is one thing here that I want to talk about that we haven't talked about yet, which is how you estimate sums. So the idea is as follows, right? If you know that something converges, you can always, so we can always approximate the sum of a convergent series by looking at a partial sum. Right? For example, let's say I know that, a series, let me just call it AN. Let's say that I know that this guy converges, right? We know that this equals some number. We don't know what it's called. Let me just call it S. Well, how would we approximate it? Well, what we could say is, well, I'm not going to go until infinity. I'm, say, going to go to the 100th term. Now, the difference is I'm not going all the way to infinity, so of course this answer is not going to match exactly, right? But of course, the further out I go, the closer it's going to get. So this is equal to, remember we call this S100. This is the 100th partial sum, and this is a way to approximate a sum. Now, the reason that we always care about how close these approximations are. In other words, what is the error? So, of course, if A1 all the way to A100 is called Sn, there's a part that we're leaving out, right? We're leaving out everything from 101 all the way to, everything else, I should say. If you add up all of those forever and ever, we call that the remainder. And so what this means is that S is always equal to partial sum plus its remainder for all n. Of course, the bigger you make n, the larger your Sn is, and the smaller your Rn is. Okay? So another way of saying this is, since the limit as n goes to infinity of Sn is the real sum, but what's also true is that the limit as n goes to infinity of your remainder is 0. Because in the long run, your remainder gets tiny the further out you go. So, how do we approximate the remainder? Well, it turns out that when you have an alternating series, we have a nice estimation theorem. We call this the alternating series estimation theorem. Okay? It says, if the sum, an alternating series, if it converges using AST, then the remainder is smaller than the n plus first term. Okay, before we do some examples on this, I want to answer this question of why. Why is this true? Well, think about that picture I drew for you guys before, okay? Let's say that we only go to the fifth case, right? Let's say we go 1, 2, or let me say I go to the third one, right? And let's say that I decide to use this to approximate my sum. But let's say that the real answer is somewhere in here. So let's say that this is S, and let's say that this guy is Sn. Okay. Well, what's the next term going to be? So the next term is this big, right? So let's say that this is, remember, Sn is right there. The very next term is going to go right here. Okay? So the point is that the error, the distance, this distance right here that we are from S to Sn, do we all agree that that's smaller than this distance right here? This would be our next term, and this would be our remainder. And so that's all this theorem is saying. All the theorem is saying is that the remainder is smaller than the n plus first term. So let's go ahead and do an example here. Now the reason I wanted to do number 4 is, so let's look back at number 4. Number 4 said, we now know that -1 to the n over n factorial is a convergent series, right? But now let's actually approximate what it is. So this will be number 5. Find the sum of this series that we did an example for. Find that sum correct to 3 decimal places. What does this mean? So correct to 3 decimal places means that we need to make sure that Rn is less than or equal to 0.001, right? 3 decimal places. As long as our error is smaller than 0.001, we know that our sum will be correct to 3 decimal places. So how would we do this? Well, all we really need to do is figure out when our terms get small enough, because by the theorem that we just wrote down, Rn is less than or equal to Bn plus 1. So all we need to do is make sure that our Bn plus 1 is smaller than 0.001. So let's look at some terms here, right? What is B1 equal to? Well, B1, if we plug that in, we get 1 over 1 factorial, which is 1. Let's keep going. B2 is equal to 1 over 2 factorial, which is 1/2 or 0.5. I'll do decimals here. B3 is equal to 1 over 3 factorial, which is 1 over 6. We're not small enough yet. Let me just keep going. B4 is 1 over 4 factorial, which is 1 over 24. Remember, we need to get smaller than 1 over 1,000, right? This is 1 over 1,000. It won't take that long to reach because factorials grow quickly. B5 is equal to 1 over 5 factorial, which is 1 over 120. B6 is equal to 1 over 6 factorial, which is 1 over 720. And let me just use a calculator really quick. B7 is equal to 1 over 7 factorial, which is 1 over 5,040. This is our key right here. Remember, we wanted to go until we were smaller than 0.001, or 1 out of 1,000. So that means that B7 is our Bn plus 1. In other words, we need to go up to 6 terms to approximate the sum close enough. So we need to write down what S6 is. S6 would be, we're starting with, remember, we're doing n equals 1 all the way to 6. So if you plug in 1, we now need to take the negatives into account, right? The first term is going to be negative, so it's negative 1. And then plus 1/2. And then minus 1 over 6. And then plus 1 over 24. And then minus 1 over 120. And then plus 1 over 720. What we're saying is that S is approximately, all we need is 6 terms if we want to be accurate within 3 decimal places. So let's see what this approximately equals. So when I put that in my calculator, I get negative 0.63. I'm going to round it to 3 decimal places. So this sum is actually correct to 3 decimal places, okay? If I want to be more accurate than 3 decimal places, I have to go out further than this, but this is my approximate answer. Thank you guys very much for watching. I hope this video was helpful.